So hello everyone, and today we are going to teach you all you need to know to win a cybersecurity research machine learning competition and make malware attacks practical. So let's introduce ourselves a little bit again. So we are Fabricio Ceschin and Marcos Botassin, and we are PhD students from Federal University of Paraná, Brazil. And as you can see in your interests, I am the machine learning guy and Marcos is the security guy. Basically, it's that. So let's introduce our work. So starting with malware detection, uh, we start asking the question, how to detect a Windows malware? So for real-time malware detection, antivirus software usually rely on static detection, where the sample is not executed, but it is analyzed using a portable executable parser. This parser is responsible for reading the data structure of a PE file that basically contains the header and the sections of the binary, where we can obtain a lot of uh, interesting attributes that can differ a malware from a good, for instance. So for instance, we can extract any executable information, such as the type of the machine that binary was developed for, and the code that will be executed, the libraries used, and the data that the software is going to use as well. So now let's talk a little bit about the adversarial machine learning. So I think, as everybody might know, adversarial machine learning is a trend in recent years. And I think many of you already saw this picture. So basically, it's a panda image that is turned into a gibbon by just applying a, a, a small perturbation to the image. So using this little perturbation, we can see that the label changed from a panda with 57% of confidence to 99% of confidence. And we cannot even see the difference of both images. It's very hard to see. But for the classifier, it is a difference. Okay, but how does adversarial machine learning work with malware detection? So, as we saw in the image classification, adversarial image should be similar to the original one, to the original image, and yet they are classified as being from another class. So the panda is transformed into another animal by a simple perturbation. In malware detection, the adversarial malware should behave the same and yet be classified as a good. So it doesn't need to look like the original malware, but it just needs to change the label to good, perform the very same action. So the challenge here is to automatically generate a fully functional adversarial malware, given that any modification can make this malware behave different. And many solutions in the literature propose approaches for that, but they are just using malware to extract adversarial features. The malware produced there usually do not work. So what we are going to share with you in this talk is our practical experience with adversarial machine learning in malware detectors. So we gained this experience during the MLSEC context, a public challenge that was created to better understand the adversarial machine learning impact in static malware detectors. As you can see in this table, we managed to win the challenge 3 times in a row. And also we managed to get insights on both attacking and defending models against attacks. So it was very interesting during these 3 years of experience what we learned. We are going to share with you now. So first, let's introduce to you the challenge. So basically, the MLSEC context was composed of 2 challenges. The first one is the defender challenge, and the second part is the attacker challenge. The objective of the Defender Challenge is that the participants develop their own machine learning defensive solutions with the models of their own choice and train it using any dataset. The only 3 requirements needed is that they must present less than 1% of false positive rates, so they do not classify goodware as malware. After all, the final user wants to use the computer without being asked all the time if a software is really a malware, right? And also, they must present less than 10% of false negative rate. So they do not classify malware as goodware. We don't want a classifier that accepts everything as a goodware. So we don't need an antivirus, right? It's the same of not having an antivirus. And finally, they must return a response within 5 seconds for any presented sample. So it's basically simulating a real-time malware detector, right? And the winner of this part of the challenge is the model that presents the fewer number of evasions in the attacker challenge, which is the second part of the challenge. So in the attacker challenge, the objective is to attack all the submitted models that met the previous requirements. These models are all available to be attacked by black box attacks only. So the attackers do not have access to their code, only the predictions provided after submitting a sample. To do so, the organizers of the competition provided all the attackers 50 unique working Windows malware samples, which participants need to modify and provide new binaries that bypass the classifiers and present the same behavior in the challenge sandbox, which are measured by indicators of compromise, which are the IOCs. Finally, the winner is in the challenge is the attacker that has most bypassed classifiers and the one that performed the lowest number of carries in case of a tie-break rule. So now let's talk about the first challenge in the 2019 challenge. So the first edition of MLSEC, there was no defender challenge. The models available were selected by the organizers. In total, they selected 3 models, which are LightBM, Malconv, and non-negative Malconv. If you are interested in these models, you can check their papers here. So you have all these 3 papers of these models. Basically, there were 2 types of models available. One type is based on parsing the PE files and extracting features from it, which is the LightBM. You can see here that given a file as input, they just extract features from the PE file, and then the model classify it in the output. So LightBM is a gradient boosting decision tree model, and it uses hashing trick and histograms extracted from the features on the PE file. In the other hand, we have the models based on raw bytes. They basically use the binary bytes as input, often end-to-end deep learning models. They do not use parsing, similar to what we have in image classification deep learning models. And both Malconv and non-negative Malconv share the same structure. The difference is that non-negative Malconv forced the model to look only for malicious evidences, which is something created to avoid adversarial samples already. So it's the first model that's trying to do something to reduce the effects of adversaries. All these 3 models were trained using the Ember 2018 dataset, which is a benchmark for many researchers in the malware detection field. It is open source and has 1.1 million portable executable files, and you can download it on the GitHub repository.
Okay, so let's finally talk about attacks, right? Well, when we started, the first thing that we have in mind was to target the Malconv model, because this is the model that relies on raw bytes. So we hypothesized that if we can add more bytes to the file, the neural networks, the neurons, you get confused by the additional bytes. So they will have more bytes to make a decision. So maybe this might work. And in fact, it's what happened, as you can see in the graph. So we started to gather random chunks of data and start to append these random chunks of bytes to the end of the malware files and try to classify them. So as you can see, as you increase the chunks of data that you append to the end of file, the model starts to classify more samples as goodware instead of malware. It happens for the malconf, but it did not happen for the other models because they didn't rely purely on the raw bytes, right? So it only happened for malconf. What's interesting to talk here about is that why it works. And this is because on Windows, when the Windows loader loads a binary, it didn't check if the binary is malformed in the sense that it doesn't control the boundaries of the file. So if the header states that that given binary file will carry like 100 bytes, but you put more bytes, the loader will not complain. Since the header is okay, the Windows will load this file. So this is why this approach works. We can add more bytes to the file, and the final result is a binary that still works, right? So I think the take-home message important here is that solving the security problem of malicious code is not only a matter of machine learning, but also a matter of security, a matter of cooperation, because even in the case that we are able to bypass these models, if the loader was not able to load this file that bypassed the model, we would have a safer system. But that's not what happens in practice. So we were able to bypass this first model just using the simple technique of adding bytes. In the next slide, I'll talk that this is not the smartest strategy to bypass a sample. A smarter approach would be not to add random bytes, but some more qualified information. For instance, strings, human readable strings. Because on security, human readable strings are very important because they tell a lot about the binary. Strings can show what was the compiler used to generate that code, the functions that are imported, the name of libraries, and so on. So it's very used in security. So we repeated the previous experiment, but now instead of adding random bytes to the end of file, we started to add strings. We collected strings from goodware files and appended them to the malware files to see what happens. And as expected, for the malconf model, it was very affected by these strings because since it relies purely on bytes, whatever the bytes are, it was affected by strings as well. But in this case, other models were also affected. For instance, the LightDBM model was also affected because although it doesn't rely on pure bytes, it checks for strings. So after a given number of strings were added to the file, it starts to classify samples as goodware. And the most interesting result, the non-negative malconf were also affected. As you can see in the beginning, it has shown the expected behavior that is not being affected by that because non-negative malconf was designed to not be affected by the addition of bytes. But what happens in practice is that there was an implementation flaw in this algorithm. In this implementation, there was an error. And after we reached a given threshold of adding strings, you can see that the result was a tragedy for this model. It suddenly starts to detect everybody, every sample as a goodware, right? So I think the take-home message here for this part is that adversarial attacks are interesting not only for you to perform, to check the robustness of your system, but it can also be used to validate your model, to check if they are working properly. So in this case, we reached the threshold when the algorithm stops working as designed to, right? Next slide, please. Okay, so let's talk about a little bit more sophisticated approach, because adding bytes and add strings is very basic. So let's do something more interesting. So let's, for instance, try to change the shape of the binary. Let's change the structure of the binary to see what happens with the classifier, right? So here I'm talking about a specific way of changing the way that the binary is structured. That's called packing. So packing is basically a way of embedding a payload inside another executable, another file that in runtime will extract this payload. So it's basically a self-extracting archive, right? This is interesting for attackers, because when you're inspecting a packet sample, you are not inspecting the payload that is embedded in the file. You are inspecting, in fact, the shell around that payload, right? So if this packer displays some strings and so on, these are the strings displayed by the packer, not by the actual payload that it has inside it, right? So it's very used by attackers. So we checked what happens regarding packers in this data set. First thing that we noticed is that there are some package samples in the data set. They are detected by all classifiers. And then we imagine to unpack these samples, to extract the payloads from these files. And what discovered for the all classifiers, as you can see here, is that their unpackaged samples are detected with less confidence than their packaged versions, right? So it seems that somehow the packers were influenced in the confidence of detection. And we also performed the otherwise experiment. That is, we take the plain samples, the samples that are not packed, and packed them with UPX, the same packers that those original samples were packed with. And what we discover is that, again, for all samples, the confidence on the detection rate increased for all samples. So the overall experiment results here show us that what was happening is that, in fact, the classifier is learning not the malicious content of the payload, but the classifiers are learning that package samples are malicious. They are learning, in fact, the packer structure, right? So this is why we have this result. And the take-home message here is that this is the challenge regarding using machine learning for security, or security as a whole, is that we do not know what is malicious. We do not know what is malware. We just know what's similar to malware, what's similar to good. So that's what the models learn. So in this case, since packers are very used by malware, the model simply learned that, okay, packers are bad. And then if something is packed, even though it's a benign file, a hello world, I will consider it as malware because it looks like a packed file. Next slide. Well, at this point, we had a problem because, as I have shown, the models have a bias towards detecting every package sample as malicious. So we needed to find an alternative. We needed to find another way to implement a packer, right? And a solution to implement a packer was to implement a packer ourselves, right? So that's basically our solution. So we implemented what's called the dropper. A dropper is a binary that embeds another binary within it and extracts it at runtime. So when you inspect it, it looks like a normal binary, but when you run it, it will drop a file in the file system and launch a process from it. And here I need to talk a little bit about Windows internals again, to talk about what's called resource. Resource is a feature of the Windows and the Windows file format that allows one to place data into the binary, whatever data. It's used, for instance, for installers to add icons that are basically images that are inserted to the binary among the instructions and among all data and extracted in runtime to create a shortcut in the desktop, for instance. But nothing prevents us to use that to carry another binary inside the original binary. So it's basically what we did. Next slide. So what we did is basically we take a malware file that's classified as malware with a given confidence by the classifiers, and we take a goodware file that's classified as goodware with a given confidence, and then we embed the malware file within this goodware file. And the final result is a file that's classified as goodware with a given confidence. And the most interesting stuff is sometimes the confidence that the classifiers have that this final result is a goodware is even greater than the confidence that they had in the original goodware file is a goodware. That's very interesting. Well, but okay, we used this strategy and applied against all samples and against all classifiers, and basically the result was that we were able to bypass all classifiers for all samples. We achieved a perfect score, right? So next slide, please. But the most interesting part is not only that we were able to bypass all the classifiers using this strategy. The most interesting part is that we did not target antiviruses we only target the models that are part of the context, part of the challenge. But a side effect was that our evasion attacks had a practical impact on real-world antivirus solutions. So in the figure, you can see the detection rate of the original samples and of the evasive samples when submitted to a collection of antivirus. As you can see here, for all samples, the detection rate decreased from the original sample in comparison with the adversarial sample. And it happens because mainly two factors. The first one is that because we are changing the structure of the file, so the antivirus do not have some rules applied by the antivirus do not match against the new file. But the second reason is that some antivirus rely on machine learning themselves, machine learning detectors as part of their engine. So since we target machine learning models in the context, we end up affecting real-world antivirus because that. And this will be very interesting. Will lead to very interesting results that I'll present for the next years. But the take-home message here is that adversarial attacks are practical, even though we were not targeting real-world antivirus. We end up affecting these antiviruses.
Okay, so now let's talk about the 2020 edition of the challenge. So this was the first Defender challenge of MLSEC, and to build our defense solution, our first thought was to use as a baseline a research model developed by us back in 2018 in a paper we submitted to Security and Privacy. Our implementation was based on TIF IDF on top of PE parsing and random forest classifier, since the PE parsing model was stronger in the past challenge. The training dataset in the paper was our Brazilian malware dataset with about 50,000 samples. And our paper reports 98% of F1 score with a very low false negative rate, which seemed a very good result. But when we tested our model with Ember test samples, which is the dataset they use it to train the samples in the last year challenge, since it was the same dataset that they used, we just used the test samples from that dataset. Sorry. Surprisingly, our model presented very bad results and totally different from what we expected, from what we reported in your paper. Because of that, we started to believe that our model was biased towards the Brazilian malware samples, which are very different from the Ember samples. Our hypothesis is that the classifiers used in the Brazilian cyberspace are not the most suitable for global samples, such as the Ember ones. And to test this hypothesis, we also trained our research model with Ember dataset. So it's the same dataset that the previous models used. Just to compare it with the one we trained using the Brazilian malware model, the Brazilian malware sample, sorry, which is our baseline model. To evaluate, we tested them with the subsets of Ember and Brazilian malware dataset, so samples that were not used to test these models, to train these models. As we can see in the figure here, the Brazilian model performed relatively well in the Brazilian malware dataset. So our baseline and the Brazilian malware dataset that we used to test, and with about 10% of false negative rate. However, the model that trained with Ember performed did not perform well in this scenario, with about 60% of false negative rate. And it's a very, very bad result in this scenario. On the other hand, when we tested both models with the samples from MLSEC 2019, which is the past edition of the context, the Brazilian model performed totally different. So we can see that it was worse than the one trained with Ember. And we concluded that the malware detection datasets and also the models are regional. So each model performs better in their own regions, which means that each region has its own characteristics, and the models need to be especially crafted for a given region. For the MLSEC context, we consider that Ember was the most suitable dataset for our model, given that the model trained with it was much stronger than the Brazilian one. So our definitive defense solution was based on features from the Ember dataset. So we basically adapted our research model to use the Ember dataset. And basically there were three types of attributes: numerical attributes, categorical, and textual attributes. As we can see here, the categorical attributes were turned into one hot encoding array, while the textual attributes were transformed into texts and used in the TIF IDF from scikit-learn. So after that, we concatenate everything and use it in the min-max scalar and train it using the random forest algorithm from scikit-learn 2. We trained our model with all the labeled samples from Ember 2017 and 2018. And we used the random forest from scikit-learn with 100 estimators, which was the classifier that performed better in our research paper. So we're just reproducing the results from our research paper here. And to fine-tune our defense solution, the objective here was to reduce the impact of adversarial perturbations by forcing classification to be more aggressive. To do so, we created a new prediction function. This prediction function uses the model class probabilities as input to determine the output using a threshold t. So if the probability of being a good year is bigger than t, it was considered a good year. Otherwise, it will be considered a malware. By using this technique with a threshold of 80%, we reduced the default random forest prediction function false positive rate from 80.5% to 0.1%. So when testing with Ember, as noted here. And finally, we, as initial test to the attacker challenge, we submitted the 2019 adversarial samples to our model. So in total, there were about 600 samples, all variations of the 50 original samples from the 2019 edition. And as a result, our model detected 88% of the samples, so about 88%. And considering that all the 2019 models were bypassed, we consider that this result was significantly good, and also confirmed our findings that models based on Parsing P files are better than the ones based on raw data, since all of them were bypassed last year with these very same samples.
All right, so let's talk about attacks once again. So in 2020, what we started doing was to repeat the steps that we performed in the first year. So we initially tried to repeat the first step, that was add random data and add strings to the binaries. And what we discovered is that just a few samples were bypassed, just a few classifiers, which shows that the models were a little bit more robust than the previous years. So they were not relying, at least not entirely, on raw bytes. So it was not very effective. So maybe the people are learning how to develop stronger models. And then we passed to the second step, that was to repeat the dropper strategy. So basically, we implemented the droppers once again for all samples and submitted to the evaluation. And what we discovered is that we were able to fully bypass the first model. So one of the models were already fully bypassed using the same strategy that we used in the first year. But there are still 2 models to be bypassed. So what we did then was try to bypass our own model, because of the 2 remaining models, one of the models was our own model that we submitted for the Defender challenge. So we were required to bypass our own model. So we hypothesized that if you were able to bypass our own model, we were able to bypass the other model as well, or at least the bypasses of our model were to influence the results of the other model. And it was a very interesting strategy because we were able to test our model offline and then just submit the samples for validation in the online phase. So it reduced the number of queries that we need to perform to test the models. So basically, we start by investigating why our own sample was detecting the samples as malicious. And we discovered that that was because the find resource function. As I told you previously, we use the resources from the binary files to embed the payloads, but it's very common in malware. And the machine learning model learned that when you are using the find resource function, it's probably malicious. So what we tried to do was to hide the import of the find resource function. That's basically what most popular packers do. After we refactored our code to eliminate the import of this function, the explicit import of this function, what we discovered was that the confidence level on the classifier that a given sample was malicious, in fact, increased and not decreased. And this is because, as I talked previously, the machine learning model learns that packers are malicious by themselves, regardless of the content. So in this case, as hiding the find resource function is very prevalent action for malicious binaries, the classifiers learned that when you are trying to hide, you are malware. So it didn't work. And then we need to find an alternative, right? Next slide. And what is the alternative? The alternative is to try to find a benign file that's classified with a given confidence that import the same find resource function. So we can try to use this detection. We can try to see what is in common between the files and try to bypass the classifiers. So we searched for a fresh Windows installation folder for files from Windows that are supposed to be benign. And we find that the calculator is a binary that imports the find resource function. And it was classified as 100% confidence of being benign. So what we had to do right now is to mimic the calculator. We need to turn our dropper into the calculator. We need to make the headers of our dropper file look like the headers of the calculator. Okay, it already used the find resource, but the calculator also uses lots of other functions and libraries. So what we have to do is to add these functions to our dropper. But we don't need these functions for our dropper operation. So what we did to accomplish that was to create a function that's never called, but that imports those functions, the same functions as the calculator. So this is called dead code. So in this way, even though this function is never called by the dropper, these functions will be present in the PE header of our dropper. So if anyone inspects the dropper, the header of our dropper and the header of the calculator, they will be the same, they will be indistinguishable. So this is basically our strategy to bypass our own classifier, mimic the calculator. So that's basically what we did. And we did it, and we succeeded in bypassing our own model. So by this time, we had already bypassed 2 of the 3 models. But there was still one model to be bypassed. And then we checked the results. When we submitted the samples that bypassed our own model against the third model, we discovered that some samples already bypassed this third model, but some didn't. And we wondered why. Because the samples were generated from the same dropper, right? So they are very similar. The only difference between 2 samples is the embedded payload. So we hypothesized that maybe this is the reason why some bypassed the third model and some didn't. Basically because the sample might be looking to the content of the dropper file in addition to the header. So following this hypothesis, basically what we did was to hide the content of the file, the content of the embedded content, right, the payload. So what we did was to employ one of the strategies that was to encode the data. So we obfuscated the embedded payload. We did it by either converting the payload using base 64, or either by changing the bytes using an XOR operation to hide the original payload. By doing it, if the detector tried to scan this file, it won't find any of the previous patterns that it was a PE file. It will just find a random number of bytes, right? So maybe it would work. And in fact, it worked. So after we did it, we bypassed the model tree completely. So we achieved, once again, for another year, a perfect match, a perfect score. The take-home message here is that performing this black box attack was a little bit harder than performing the offline attack because we needed to hypothesize, we needed to guess, but it's not impossible. So it was even possible to identify which feature was being used by the model. That in our case was the content of the file due to the difference. So if one tries to submit samples with very little difference among them, maybe someone will be even able to discover which features are being used. So black box attacks are even possible. All right, so this is the result. As I told you, we achieved the perfect score. But I think what's more interesting to talk here about is the average number of queries. As you can see here, we used then less queries on average per sample to be able to bypass that sample. And I consider this very interesting because it will probably not raise alarms when used in a real world setting, right? Because suppose that you have an intrusion detection system and someone is performing a port scan against you. This detection system will probably not raise an alarm just after the first time someone knocks on your door. It will probably raise an alarm after someone has knocked on your door many times. So this is probably the same for any machine learning-based system. So if someone is monitoring the system will probably not raise an alarm after the first time you try to bypass it, you try to probe it. So I think 5 times is enough to not raise a warning. So maybe it's possible to perform this kind of attack without being noticed. So I think a good metric we can use in our future research or future papers or whatever, it's how many queries needed to perform to bypass a model. Because if we have 2 models that are similar in accuracy, precision, or so on, I would prefer the model that's more robust against evasion, the model that takes more time to be evaded because it gives to the defender more time to react to it, right? Next one. Well, once again, as in the previous year, we tested the side effects on antivirus solution. And as you can see here, once again, the modifications we performed in the malicious files resulted in decreasing the detection rate by real antivirus. And in this year, the detection rate decreasing was more noticeable because now, in addition to change the format of the file, we were hiding the content. We are hiding the payload embedded in the droppers, right? So the antivirus didn't have much to scan in that file. So it significantly decreased the detection rate. Next. And interesting is that this result is true even for those antivirus that use only machine learning. There are some antivirus they are basically machine learning models in the form of antiviruses. And for all of them, as you can see here in the table, you were able to either flip the classification class to change from malware to goodware, or in the worst case, at least we were able to reduce the confidence in which a classifier has that something is malicious or benign. Next. A side effect that I haven't talked about yet, but I'll talk right now, is that antivirus not only present a detection rate as a result of their scans, but they try to cluster the samples among similar ones to try to provide you with some more significant information. Like, okay, you submitted this sample, these samples look like a banker malware, look like a password stealer, or look like a botnet. So antivirus try to classify samples among the things that they know and assign labels to them. In the figure in the left, you see that the labels assigned to the original samples. There are many families, they are somehow well balanced. And the figure in the right show what happens when you check the labels for the adversarial settings. As you can see here, there's a prevalent class, right? There's a prevalent label that is assigned to most samples. And this happened because, as I've talked about this entire presentation, we do not know what is malicious. In fact, we just know that something looks like malicious, something looks like something that we previously know. So basically the antivirus, as well as the machine learning models, were just putting all the droppers together because they have the same structure, they look all the same, but in fact their content is very different. Next. And this result is also true if we look at the byte level, if we check the structure of the files. So if we take a similarity hashing function that produces a digest based on the bytes of the files, we can see in the left, in the beginning of the x-axis, the original samples were not very similar. They have a reasonable amount of similarity, a reasonable score of similarity. And the right of the figure, we have the similarity, the byte similarity of the adversarial samples. You can see here that once again, what the similarity hashing function is displaying is that the files are similar in the form. They use the same bytes, they have the same structure, things are placed in the same place, but they cannot tell you what's the content, what's the goal of that file, right? So this is a problem either for machine learning models, for real AVs, or for similarity hashing functions. So this is the problem we have to face when handling malware.
Okay, so now let's talk about this year contexts. So our defense solution this time was based on our previous model with some improvements. Some of these improvements are based on the insights we gained during the last year context. And so first we removed all the features related to strings, because we know that strings can make the model less resistant to string-based attacks. Also, we used some more textual attributes from Ember that we did not use it in the previous year, such as the port list, the DLL characteristics list, and the characteristics list. And finally, we also changed our feature structure to hashing vectorizer, which made our classifier more resistant to attacks. In addition, for online learning procedures or real-world solutions, this method does not require to update the vocabulary as time goes by. So as new malware comes, we will not need to train this model in practice again. So this feature structure again. That's one advantage of using it instead of TIF IDF. So as an initial experiment, we tested 3 different approaches with the MLSEC 2019 and 2020 adversarial samples as a malware, and we used pristine Windows apps as goodware. When tested with the MLSEC 2020 model, we obtained a very low F-score and recall, as we can see in the table. An improvement can be seen with the very same model, but without the string features and new textual features we included. So from 0% to almost 21% of F-score just by doing this little change. And now when we test it with the new 2021 model, which uses the hashing trick without string features and with more textual features again, we obtained 43% of F-score. So it was from 0 to 43, it's quite a good result. So it's important to note that all the classifiers have a high precision. So this indicates that they detect all Windows apps as being a goodware. The only problem here is that to detect, in fact, malware, because the recall is quite low. So to tune our solution to improve this problem with recall, we consider 2 factors. So the training data set, we consider 3 different sets, all of them containing the Ember labeled samples. The only difference here is that one of these sets includes the MLSEC 2019 adversarial samples, and another the 2020 adversarial samples. And also we also changed the model threshold once again to see which threshold was the best for this context. So by evaluating the threshold and using the first dataset, which is only the Ember dataset, we created this figure, which uses the MLSEC 20 19 and the 2020 as test sets. So all experiments from here, we use this set as tests. Note here that we have very high false negative rate and become very closer to zero when we increase the threshold to about 85%. Without increasing too much the false positive rate. So it seems quite a good result in this point, even though the threshold was quite high. In the second data set, when we use the MLSEC 2019 adversarial samples, almost everything is considered a malware. So the more we increase the threshold, the more the false positive rate increases. So it was not the ideal solution for the challenge. So we did not consider this model and this data set to train our model. And now when we use the MLSEC 2020 adversarial samples with Ember, we notice that the false positive rate and the false negative rate were more balanced. With just an increase of the false positive rate, the more we increase the threshold. So we see here that is a little bit better than the other models we trained. So for this challenge, we choose the 75% of threshold. And that is what happened in practice, because if we compare our model with previous editions, we can see that it presents much less false negative rate than the others, because it was much more aggressive than the other editions, other models, because almost everything was considered a malware again. So because of the adversarial samples we trained it and the threshold that we increased it, we can see the false negative rate is much lower than the other two models. And it's even more clear when we see this chart analyzing the false positive rate on multiple Goodword data sets. So we tested all of these three models in different Goodword sets, and we can see that our 2021 model presents a very high false positive rate in many different Goodword data sets. So only for the pre-seen Windows apps it was low, and for all the others it was, the other models were much more reliable in practice than our 2021 edition model. We believe that our model classifies everything that is slightly different from a pre-seen Windows apps as a malware, given that any other Goodword from other sources are in majority considered malware, as we can see in the figure. Again, we want you to note that the dataset characteristics matter again, and as a recommendation for future works, we want to say that test your malware detector with as many datasets as possible, so this thing won't happen. Finally, as we can see in the table, our model presented the smallest number of bypasses ahead of all other participants. So it was another win for our team, despite of considering many samples as being a malware. So it was good for the challenge.
Okay, so let's talk finally the last year, so this year solution. Once again, we started by hypothesizing that if you are able to bypass our own model, you are able to bypass other people's model. And we started repeating our strategy. But there was a problem, because since this model has a bias towards detecting everything as a malware, we were not able to find any Goodware file, even within the Windows folder, that imports the local resource function, the find resource function. So we were not able to mimic the calculator anymore this year, because our own model prevents that. But we find another bias from our model that's detecting DLLs, dynamic libraries. So we found that libraries were less detected as malware in our model, and we tried to find a library that is detected as Goodware, as in the previous year. And we found that NTDLL library is detected as Goodware with a reasonable confidence, and we tried to mimic it. But right now, instead of mimicking dead function import, we had to mimic dead function export, because it was a library, so it's not importing function, but exporting function. But in the end, it's the same stuff. And then we implemented that. We converted our dropper to a DLL, and it worked in our tests. So we were happy because we were able to bypass our samples once again. And then we noticed that there's a new rule in this year challenge. That is, oh, no droppers allowed, which means you can't drop files to the file system that are detected. And I think this is very important to discuss because what's the rationale behind it? In the beginning, we had a malware that was detected by a machine learning classifier. And then we embedded this malware into a dropper that was not detected. But when we run this dropper, it drops in the file system the original malware. So if we run the machine learning classifier against the dropped file, if we had a system monitor, like a file system monitor or an antivirus that continuously monitor the system, it would be able to identify that a file was dropped in the file system and launch the machine learning classifier against that file. And since that file was the original file that was originally classified as malware, it would be detected. So this is why they did not allow droppers this year. And this makes sense. And this shows again what I was talking in the beginning, that solving the security problem is not only a matter of hardening the classifier, but a matter of cooperation between machine learning and security stuff like real-time monitoring. Because even though we were able to bypass the classifier with an adversarial attack, we would not be able to infect a system that's monitoring real-time with a solution that continually resubmit the dropped files to the machine learning scan, right? So this is a matter of cooperation, and we should invest in it. Next slide. Okay, so we needed to find alternatives, right? Since we are not allowed to use our file system dropper. So there are two alternatives. Either we do not drop anything in the file system, or either we drop a file that is not detected. And we tried the first attempt, we tried to perform an in-memory attack. That's basically, we would still embed the payload, but instead of dropping to the file system, we would launch a process or take a running process, a Goodr process from the system, and drop our payload directly to the memory of that process. We would patch the process memory, right? This is our approach. So we would run the process, we would resume the execution from the originally launched process, but now with the payload, with the memory code from the malware file. And then that process would behave as malware. So this is our strategy. And we implemented it and executed it. It worked locally, but when we submitted, it didn't work in the context sandbox because they used a distinct file, a distinct process, and this process didn't like to be injected. So what we needed to find was a solution. We needed to find a process that likes to be injected. It means it does not crash when you patch its memory. And then we started to search again for bias into our model to identify what we could do. And then we started the second step. That was basically, we identified a file that we can drop in the file system that is not detected, or I mean, is detected as Goodr, but that can have its memory patched. And what is this file? This file is .NET files, because once again, we discovered that there's a bias against some types of files, and especially in the .NET case, we discovered that as for packers, for the .NET case, the machine learning model also learned the structure of the .NET file and not the content, because the .NET file imports only one library. That's basically the .NET runtime. So the machine learning classifier learned that every file that imports the machine learning runtime was a Goodr. So we benefited from it this time to implement a hello world application that's not detected by any classifier, that is dropped by our solution in the file system. A process is created from this file. So we create our hello world process, but then we patched this hello world process with the malicious content that was embedded into our file. Next slide. So using this strategy, we were able to once again win the competition. And this time we used even less queries than the first time. We were not able this time to bypass all samples because some samples were not good for memory injection because, for instance, the original sample invokes itself from the file system. So since we are not writing to the file system, we are not able to run the sample. But from all samples that are okay, that does not use file system actions, we were able to convert them to memory payloads. Next one. To test our hypothesis that bypassing our model was enough to bypass our models, we compared the results of each classifier. And as you can see, our own model was bypassed 32 times. And as you can see, the other models were bypassed almost the same number of times. Sometimes one or two samples failed due to multiple reasons, but this hypothesis was true in most time. For the second model, it has more bypasses because it was also vulnerable to the first strategies that I presented, like appending strings or random bytes, so it was bypassed more times. But overall, bypassing our model was enough to bypass the other models. And once again, as a side effect, antivirals were affected. So as you can see, in the case of the first sample, for example, we had a detection rate of around 80% on the original sample. And after we modified it to be embedded in a dropper with a memory payload, the detection rate was about 20%. So sometimes the result might be very significant. And then we claim once again that this kind of attack is practical and is viable, and we must pay attention to it.
So finally, let's conclude our work. So as noticed by our experience, adversarial attacks really happen in malware detector, and they are very effective. So they must be taken into account in threat models, datasets, and experiments. To encourage this practice, we publicly released our codes to the community. Tools anyone may be able to practice and also improve them, please. Also, anyone can consider adversarial attacks in their own research. And we also released a web-based solution to generate adversarial samples with our method and test them in multiple machine learning models to check the robustness and the viability to attack them. You can check our web-based solutions in the Corvus website here. So if you're interested, please visit this website. So here's a video, but I won't play it due to the time we have. But I think if Heitor sent the PDF, you can see this video. And finally, as a feedback for future work, we believe that our findings are valuable feedback for next generation solutions. Since embedding payloads into binary, it's simple and yet effective way to defeat classifiers. The future solutions cannot be limited to look only into the first layer of the binary. They need to find a way to extract embedded payloads and classify them somehow. And also using new features representation would be great to cover less mutable features. And after all, as everybody saw in the machine learning classes, features need to be discriminative and invariant. So it's something very important that we need to consider in cybersecurity as well. So here are our GitHub repos for the challenge. So if you're interested in attacking or defending against attacks, here's our codes. And also here are some papers related to this work. We are open to collaborations. If you are interested, please contact us. So that's all. Contact us if in your Twitter or email if you're interested in discussing something. And thank you very much for watching us, and especially thanks to Heitor who contacted us for this talk.